Our journey today will give us valuable insight into the principles that guide effective data visualization. Let's get started. By the end of this lecture, you will be able to explain the foundational principles of effective data visualization and describe how each serves honest, efficient communication. Select the appropriate chart type for a given dataset and analytical goal. Diagnose misleading visualizations by calculating the lie factor and identifying scale distortion, chart junk, and dual axis manipulation. Critique the real world charts and dashboards by auditing them against design principles and proposing evidence based remediation for clarity, integrity, and accessibility. Data visualization isn't just about making charts visually appealing. It actually involves three fields: statistics for the data, cognitive psychology to understand how people interpret visuals and values, and graphic design to effectively present information. When these disciplines combine, raw data becomes a powerful visual story that informs decisions and highlights insights quickly. However, it is essential to realize that neglecting these principles can lead to visualizations that mislead rather than inform. They can exaggerate small differences or hide significant trends. In this lecture, we will establish the theoretical groundwork to ensure every chart you produce is both truthful and impactful. Let's get started. The most influential thinker in this field you should be aware of is Edward Tufte. His books, especially the visual display of quantitative information, are essential reads for anyone working with data seriously. His core idea is perfectly captured in a memorable sentence: above all else, show the data. While it sounds simple, its meaning runs deep. Tufte highlights that every design choice should prioritize the data rather than aesthetic taste, your client's branding, or just making things look impressive. Let's explore one of Tufte's most practical ideas: the data ink ratio. Think of every pixel on your screen as a tiny ink drop. Now ask yourself, does each ink drop directly show data, or is it just there for decoration? The data ink ratio helps to answer this. You calculate it by dividing the ink genuinely used to display data by the total ink in the entire graphic. A ratio of 1 means every pixel is working hard to convey information. A lower ratio indicates that you might be distracting your audience with visual clutter. Common culprits include heavy grid lines, 3D effects, thick borders, gradient backgrounds, and drop shadows. None of these add to the data itself. In fact, they can distract or confuse the viewer. Your aim should be to cut these elements out as much as possible, creating cleaner and more effective visuals. Wondering how to make your chart clearer and more inviting? Start by reviewing your axis. Most software automatically surrounds your plot with a border. But ask yourself if all four slides are truly necessary. Often, removing or lightening the top and right borders can make a big difference without losing any value. Also, be intentional with your use of white space. Negative space isn't wasted, it helps separate elements and guides the viewer's eye naturally. And here's a game changer. Consider ditching the legend altogether. Instead of a separate color key, label each data series directly on your chart. This small change reduces eye movement and keeps the viewer focused on the data itself. These simple tweaks help draw attention right where it should be, on the numbers, making your chart both beautiful and easy to understand. Let me introduce you to one of Tuftay's most well-known ideas, chart junk. Chart junk includes all the unnecessary visual elements added to a chart that don't actually reflect the data. You have probably seen it before. Thick cross-hatched files like these that you can see here with multiple types of all these different shades and colors and lines. So 3D effects on simple column charts or dashboards with a stock photo of gears on the background, very unnecessary icons. These might seem to make the chart more lively or professional, but they don't. As I told you, always perceive it through the eyes of the observer. It's very clear, decorative touches often distort the data they are meant to showcase, and no amount of styling can replace the solid analysis. If your statistics feel dull, it is worth evaluating your data, not adding more effects. Simplify your chart. It will focus on the important data. According to Tuftay, the essential rule for any data graphic is very straightforward. Do no harm to the data itself. Now take a look at this chart and point out 5 things that you see as chart junk. Now let us look at a very interesting chart which is called small multiples. It's incredibly effective when it comes to showing large number of data. Instead of stuffing multiple data series into one cluttered and confusing chart, you set up a grid of small matching charts. Take a look at these charts. Each one displays the same variables but for different slices, like different times. Now these are times. It can be countries or products as well. The beauty of this approach is that since every panel looks the same, like in this case, all looks the same, your audience only needs to learn how to interpret it once. Now, for example, if you know how to interpret this chart, all of the other charts, the smaller ones, are all following the same structure. So, after learning how to interpret one, the audience can quickly scan the entire grid, effortlessly spotting pattern changes, anomalies, and trend differences. You can observe this one as a clear increase of values, and this one as a clear decrease. It turns complex multivariate data into a visual experience that is easy for your eyes to understand intuitively. Small multiples tap into the human eye's greatest strength, perceiving differences within a steady, familiar framework. Think about this example. If one school student wears a different uniform, you can easily spot that student. Here we talk about the spark lines. So they are data at word size. Look at the symbol here, the name, and the daily change, rate of change, and the close history. A lot of information has been gathered into a simple, viewable area. Spark lines are such a beautiful, simple way to capture the essence of data. They are tiny, compressed charts that fit effortlessly inside a sentence or a table cell, about as wide as a word. You can see they are very nicely fitted into the table. Despite their small size, they pack a punch by showing trends and volatility at a quick glance, something a single number can't quite do. Imagine a financial table with daily stock closing prices. A number shows where the stock ended today, but a spark line right next to it, like here, reveals the entire year's journey in just one character. Instantly, you can see if it has been climbing steadily, like in this case, bouncing wildly, or gently drifting downward. Spark lines are perfect for dense data tables that need to stay compact but still tell a clear visual story. They beautifully prove that you can have rich analytical insights without sacrificing space. It's a lot of things compacted in very small space. Now let us do a simple activity. Look at this chart here. You can see a matrix of scatter plots, what we call a scatter plot matrix, a grid that shows every pairwise combination of a set of variables at once. Do this activity now. Put the things that you can see into the fill in the blanks activity. Now let's talk about an important concept in graphical integrity, the lie factor. The concept of lie factor serves as a quantitative measure of how much a graphic distorts the underlying data. To calculate the lie factor, you must first define the two size of effect values. The first component is the size of effect in data, which is the actual percentage change or difference between the values you are comparing. The second component is the size of effect in graphic. This is the percentage change between the physical measurements like the area or length in pixels of the graphic elements that represent those values. Calculating the lie factor means measuring the visual effect size, which is the perceived change in the graphic, and dividing it by the real change in the data. A truthful chart has a ratio exactly at 1.0. When the lie factor exceeds 1.05, it indicates exaggeration, often due to the use of 3D effects or area scaling for 1D data. Conversely, if the lie factor drops below 0.95, it suggests an understated visualization, which can happen because of truncated access or inconsistent scaling. Understanding these factors helps ensure our data visualizations are balanced and trustworthy. For instance, if your lie factor is 14.8, It means your chart makes the change seem nearly 15 times larger than the data indicates. Importantly, high life factors are always intentional. They can result from careless design, default software settings, or naive use of 3D graphics. Regardless of intent, the effect is the same: misleading your audience. You are now responsible for preventing such distortions. Let's look at a simple example to understand the concept of live factor further. In this example, we have a chart showing website traffic. We can see a very high difference between January and February data. The chart also reveals that the y-axis is truncated. Now, if you calculate the actual value difference and the virtual bar heights in pixels, we can calculate the live factor. As you can see in step 3, the live factor is equal to the ratio between the visual effect and the data effect. I'm not going to reveal the actual answer here, but you can calculate it and let me know what the answer is. Also see the live factor value and its meaning in the table. This is a published graphic that showed American car fuel economy standards increasing from 18 to 27.5 miles per gallon. Let's look at this. In 1978, this width indicates the miles per gallon, and this is the miles per gallon in 1985. This change in fuel economy is roughly a 53% change in actual data. Let us now see the live factor in this visualization. We now walk through a live practice version of the fuel economy live factor calculation, building on the same published graphic from the previous slide. The graphic line length is 1.93 centimeters for the earlier year and 18.26 centimeters for the later year. Before we do any maths, does this look like an honest one-to-one representation of the change in fuel economy? Or does it already look exaggerated? Let's take some moment to answer. Calculate the size of effect in graphic. Percentage change is equal to 18.26 centimeters minus 1.93 divided by 1.93. So what is the answer? Now this is only half the formula. We need to calculate the size of effect in data as well. Put the two numbers together. Live factor is the size of effect in graphic divided by the size of effect in data. With the graphic effect at roughly, calculate yourself, and the real change at 53%, the live factor comes around close to 16. Small differences come from how precisely the line lengths were measured on the original graphic, so this can change, but very slightly if you measure it by your own. Any live factor this far above 1.05 is counted as a seriously exaggerated graphic. It's misleading. Let us now look at a classic oil barrel example. A 3D graphic used to show the price change, which ends up distorting the data far more than the 2D line examples we just discussed. The real world barrel volume is constant, 42 US gallons or 159 liters roughly. Now, the price has changed between 1973 and 1979, but the graphic changed both the height and the diameter of the barrel, drawing to represent that one price change. Let's look at this in detail. Let me ask you a question. What is the perceived volume difference of the two barrels? Since the artist scaled both height and diameter, the barrel's visual volume, not just its height, is what viewers perceive, and volume scales with the cube of the linear dimensions. Calculate the perceived volume difference, which is the graphic effect. And now, what is the lie factor? Size of the effect in the graphic divided by size of the effect in data. You can see how large the lie factor is. We need to remember two takeaways from this. Never encode one-dimensional data, a single price figure, using a 2 or 3-dimensional shape, because area and volume distort perception non-linearly. Flag that the dollar figures are nominal, but inflation adjusted, a separate and equally important integrity issue is there. It is worth raising even after the lie factor is resolved. One of the most common ways people are fooled visually is by a truncated y-axis. And it is really important to spot this. When it comes to bar charts, there's a key rule. The y-axis should always start at 0. Bar charts rely on the length of the bars to show the differences clearly. When you cut off or truncate the axis, the visual representation can be misleading since the proportions of the bars no longer accurately reflect the actual numbers. Imagine product A here scores 950 and product B is scoring 1000 on a satisfaction survey. That is roughly a 5.3% difference. Now, if the y-axis begins at 900 instead of 0, product B's bar looks twice as tall as product A's, giving the illusion of a 100% difference, even though the actual difference is just about 5%. You will often notice this in political ads and financial marketing. Line charts are a bit more versatile. They show data through position and slope rather than bar length. However, it is important that the axis truncation is clearly labeled and not designed to deceive the audience. Let's now explore how our brains make sense of visual information through Gestalt psychology. This was developed by German psychologists in the 1920s. This is a very interesting area. How does the mind take a jumble of dots, lines, and shapes and instantly organize them into a meaningful picture? The key discovery is that our brain is naturally a pattern-seeking powerhouse. Instead of painstakingly analyzing each element one by one, it quickly looks for the simplest and most coherent interpretation of what we see. This remarkable tendency is called Prägnanz, roughly translating to good form in German. When it comes to data visualization, understanding this innate process can be incredibly powerful. By knowing how our brains automatically group and organize visual elements, we can craft charts that guide viewers' attention exactly where we want, all without adding extra labels, text, or clutter. Essentially, Gestalt principles act as a helpful guide for designing visuals that are easy to perceive and understand. Proximity is the simplest and most used principle in this area of visual encoding. Elements placed physically close together are read as one group, with no border required. In a group bar chart, keep tight spacing between bars within a category and a wider gap between categories. The spacing alone tells the eye where one group ends and the next begins. In the case of similarity, elements that share color, shape, or size are perceived as belonging together, even when they are physically far apart on the page. This is proximity's complement, working across distance instead of within it. Practical rule is to pick one color for a given variable, say for example revenue, and reuse that exact color every time revenue appears on every chart, on every page of a report. This is a very interesting thing. If you follow, you will realize viewers can then track that variable across multiple charts without rereading a legend each time. The next point is continuity. The eye naturally follows the smoothest, most continuous path through a set of points, which is the entire perceptual basis for why a line chart reads as a trend rather than a scatter of unrelated dots. The same principle explains aligned table columns. Once numbers line up vertically, the eye looks onto that straight path and flows down the column on its own. Think about reading a table. So drawn vertical grid lines add nothing but non-data ink when you follow the continuity principle. Eye will always follow the continuous path. Another important Gestalt principle is the closure. The brain automatically completes a familiar shape from incomplete visual information. This is why a chart can drop most of its bounding box, just a partial x-axis and y-axis, or even neither, and viewers still mentally see the missing frame. Minimal access are enough on most scatter plots and bar charts. A full four-sided border is rarely necessary, and for the data ink ratio is usually ink better spent elsewhere, or remove those unnecessary lines. Another important concept is enclosure. A shared border or even just a light background tint reads as these items belong together. A stronger grouping signal than proximity alone, because it doesn't rely on spacing. Shade a soft gray rectangle behind a cluster of points or behind a specific time window to call attention to it without adding a hard-edged box that would compete visually with the data itself. You can do that and see the contrast it gives. Now let's look at a very important Gestalt principle, the connection. It is the strongest Gestalt grouping cue of all, stronger than proximity, similarity, or enclosure. A physical line drawn between two elements is read as these are directly related, almost instantly, with no extra explanation needed. Think about this. When you see this connected line, you automatically understand that they are in one group and they belong to each other. This is the entire logical foundation of both line charts, points connected in sequence like this, and network or node diagrams, nodes connected by an edge implying a relationship. Why does removing the connecting lines from a line chart make it feel like unrelated data? That is because you have removed the strongest grouping cue available, the connection. The brain automatically splits any scene into a foreground figure and a background figure. This is known as figure ground. You can't help but decide what's the subject and what is just the context. In chart design, make sure the data is always unambiguously the figure. Keep backgrounds plain and low contrast, and reserve your strongest color and contrast for the data marks themselves. A busy background or heavy grid lines fight the data for figure status and slow the viewer's cognitive understanding down. Another interesting concept is the symmetry. A symmetric layout feels ordered, stable, and intentional. Asymmetric layouts read as unfinished or accidental, even when they contain the same information. Use this for page level layout decisions, centering a title, balancing panels on a dashboard, etc. You can think about many things. But caution is always important. Do not let symmetry override the encoding rules that we discuss. The shape of a chart should still be driven by position, length, accuracy, not forced into visual balance for its own sake. Now let's look at a simple comparison. Pre-attentive attributes are features of a single mark, such as color, size, or position, that our brains recognize quickly in about 250 milliseconds, even before we consciously notice them. Meanwhile, Gestalt principles help us understand how our minds group multiple marks together into a whole picture. One aspect addresses what do I notice first, while the other considers what do I see as related. When designing charts or dashboards, using both of these approaches together creates clearer, more engaging visuals. Now we have a genuine question. Following all this, how do we select an appropriate chart to show the data that we have? It is confusing, right? To answer this, Cleveland and McGill in 1984 laid the empirical foundation for chart selection. Their conclusion is that graphs should employ elementary tasks as high in the ordering as possible. What does it mean? This is why bar charts outperform pie charts. Bars are more towards position, pies are more towards angle. The chart you see here was generated by Here and Bostock via crowdsourcing in 2010. They have asked about different questions from different audience to find out the hierarchy of the visual elements. They proved that position along a common scale like a bar chart is the most accurately decoded visual. The angle is less accurate, hence the pie charts can be misleading. Area and color shading like pie charts and choropleths are decoded the least accurate. The design rule is simple. Always employ encodings as high up that hierarchy as your data permits. Let's look at some key principles of effective data visualization together to conclude. Minimalism, as software suggests, is all about maximizing the data ink ratio, meaning we should remove chart junk, unnecessary borders, legends, and grid lines, so that every pixel truly serves to convey information. Graphical integrity is crucial, and using the lie factor helps us spot distortions like truncated axis, 3D effects on 1D data, or non-zero baselines that might mislead the viewers. Understanding perception science allows us to design visuals that tap into pre-attentive attributes such as color, size, and position, which our brains read in about 250 milliseconds, as well as Gestalt principles like proximity, similarity, and closure that guide the viewer's eye smoothly through the data. And at last, Grounding our choices in empirical research, like the Cleveland and McGill hierarchy from 1984, helps us select the most accurate encodings for our data, with position being the most precise and color or area less so. Let's meet in our next lecture.